Okay, so what if I told you there's a kind of secret code, a language that describes everything that moves, from a planet orbiting the sun to you just walking down the street? Well, today we're going to start decoding that exact language. And we're starting with the most basic idea of all, motion in a straight line. So, to get our heads around this, we're going to follow a really simple story, one taken right from our source material. It's just a kid walking from home to school. Super simple, right? It's a journey we've all made 1,000 times. But you'll see that physics looks at this walk in a very, very specific, and honestly, a pretty powerful way. So if I asked you to describe that journey, you'd probably say something like, well, they walked from home to school. And hey, you wouldn't be wrong. But that simple answer, it kind of hides a much more interesting story. To tell that story, we need a more precise vocabulary. So the real question is, how do we actually describe this journey in the language of physics? And that question brings us right to our first big idea. And it's all about the path you take versus the point you end up at. Now, I know that sounds like the same thing, right? But trust me, as we're about to see in the world of physics, they are worlds apart. All right, let's actually trace the path the child walked. So they leave their house, they go down the block, they take a right turn, then another left. If we were to add up every single one of those segments, the total comes out to 700 meters. And that right there is the distance they covered, literally every single step they took. But is that the whole story of their journey? Not even close. See, that 700 meters tells us how much ground they covered, sure. But it doesn't tell us the most important thing. Where did they end up compared to where they started? There's got to be a better way to talk about that, right? Okay, so what if we just ignore that winding path for a second? Forget all the turns. Let's instead draw one single straight line, as the crow flies, from the start point, the house, directly to the end point, the school. This direct route, well, it tells a completely different story. And how long is that straight line? Get this. It's only 500 meters. So now we have two different numbers for the exact same journey, 700 meters and 500 meters. And the crazy part is, they're both correct. They just mean very, very different things. And this is where the language of physics gets super precise and powerful. Okay, so this whole thing brings us to two absolutely crucial terms in physics, distance and displacement. That 700 meters we talked about first, that's the distance. It's the total path you traveled, the whole shebang. But that 500 meters, that's the displacement. It's the straight line change in your position from start to finish. And here's the kicker. It's not just a number. It's 500 meters in a specific direction. I love this way of thinking about it. Think of these two ideas as two different families. You've got the scalars. They're kind of like just the facts family. They give you a number, and that's it, plain and simple. But then you have the vectors. They're the details family. They also give you a number, but they always bring a +1 to the party. Direction. All right, let's make that official then. A scalar quantity is described only by its magnitude, basically how much of something there is. Our distance is a perfect scalar. So are things like speed, mass, or time. It's just a number, that's all. A vector quantity, on the other hand, well, it needs both magnitude and direction to tell the whole story. Our displacement is the perfect example here. It's not just 500 meters. It's 500 meters along the line from A to D. And you've got to remember this distinction because this simple but brilliant idea is the key to everything else we're going to talk about. Okay, awesome. So now we have a way to describe the journey's path. We have distance and displacement. But what happens when we bring a clock into the picture? As soon as you add time to the mix, we unlock our next big distinction, the difference between speed and velocity. So, remember our just the facts scalar family? Well, speed is one of its members. It's super simple. It's just the rate at which you travel a certain distance. So it cares about that entire 700-meter path our student walked, but it doesn't care one single bit about which direction they were facing. Velocity, on the other hand, is a proud member of that details vector family. It's the rate of change of displacement. And think about it. This makes perfect sense. Since displacement has a direction, velocity has to have one too. It's all about how quickly your position is changing along that straight line from your start to your finish. But let's be real for a minute. Most journeys aren't perfectly smooth, are they? In the real world, we speed up, we slow down, we stop at traffic lights. So how does physics describe a journey that's, well, kind of jerky? You know, when you're constantly hitting the gas or tapping the brakes. Okay, so first, look at this. This is a perfectly smooth ride. Just look at the data. Every single second that passes, the distance traveled goes up by exactly 3 meters. From 3 to 6 to 9 to 12. It's totally consistent. It's predictable. This is what physicists call uniform speed. Okay, now look at this trip. This looks a little more like my morning commute, doesn't it? In that first second, it travels 3 meters. Okay, fine. But in the next second, only 2 meters. Then it speeds up and covers 4. The speed is all over the place. It's changing constantly. This is what we call non-uniform motion. And, you guessed it, we need a special word to describe that change. And that word, of course, is acceleration. Acceleration is the special tool physicists use to measure how quickly your velocity is changing. Now listen closely, this is important. It's not about how fast you're going. It's about how fast you are changing how fast you're going. It's the rate of change. And yeah, it totally works both ways. If you have a positive acceleration, that just means you're speeding up. Your velocity is increasing. If you have a negative acceleration, something we all call deceleration in everyday life, it just means you're slowing down. Simple as that. You're still moving, but your velocity is getting smaller. Okay, so let's just pause for a second and take a step back. Let's look at the beautiful, logical system we've just built together. This isn't just a random list of vocabulary words. No way. It's a complete language for describing motion, where every single piece builds perfectly on the last one. I mean, just look at how elegantly this flows. We start with the absolute simplest question. How far did you travel? Boom. That's distance. Then we get a little more specific. Okay, but where did you end up compared to where you started? That's displacement. Then we bring in the clock. How fast did you get there and which way were you going? That's velocity. And the final layer, did that velocity change at all? And that, my friends, is acceleration. See? It's a perfect logical progression. And here's the really incredible thing. These 4 concepts we just walked through, distance, displacement, velocity, and acceleration, they aren't just for explaining a kid's walk to school. No, this is the fundamental code. This is the language used to describe the motion of planets, of entire galaxies, of literally every single thing that moves in our entire universe. So the next time you're in a car, or just taking a walk, or even just watching a leaf fall from a tree, pay attention, listen closely, because now you understand the language that motion speaks. So my question to you is, what stories of distance and velocity and acceleration can you now see unfolding all around you?